So start recording. Right. So today we're going to continue with some of this section which deals with operational amplifier applications. We looked at some last week, like the precision rectifier on various configurations of those. We did some comparators. So this week we're going to have a look at waveform generators. All right, and which are particularly useful applications of the op-amp, and it allows us to generate a set of signals that are useful in any number of applications that you might want to think of. Today, we're going to look at what is termed broadly as multivibrator circuits. And there are three sort of categories of it. At any time, of course, feel free to stop me for clarification, and I'll go back over the material as required. All right. So the multivibrator, as the name implies, is something that is changing states and producing some sort of output for us, some sort of changing state output. And there are three sort of variations of that. One, which is the astable, or sometimes people call it astable, depending on which part of the world you come from. But the astable multivibrator is not stable in any state. In other words, the output, remember we're talking about an op-amp here, right? So we have the output here. And the output for the op-amp, unless you do something significant to it, meaning put resistors and so on in it, the output can either go to plus or minus VSAT. And VSAT, of course, is determined by whatever the specs of the op-amp, the particular op-amp say, right? We covered that some op-amps that VSAT may be within 1 to 2 volts of the plus or minus VCC. And in some cases, there are operational amplifiers that get VSAT right up almost to plus or minus VCC. All right. So in the case of the astable, the output changes from positive to negative and back at a predetermined rate. So it's not going to stay in either VSAT or minus VSAT permanently. It goes from one, then to the other, then back to the other, and so it keeps going on. In other words, it's going to give you a kind of square wave behavior. The monostable is stable in one state, the mono part. Mono single, so it's stable in one state. So it stays in a particular state and will stay so forever, or unless you turn off the power. And if you do something to it, it will enter another state and stay there for a short while and then come back. So meaning it will sit down in, for instance, minus VSAT or plus VSAT, and it will stay there indefinitely. But if you do something specific to it, the output will change to the opposite polarity and stay there for a little while and it will clear itself and then come back to the stable state. And then the bistable is one that stays permanently in either state unless you do something to it. So if you were to sort of look at the waveforms, the astable gives you a sort of waveform that is going to look like that. Right, this is plus VSAT minus VSAT, right? And it's going to change back and forth at a predetermined rate, and we're going to see how to do that. The monostable is going to stay at some state, and then when you do something to it, it goes from, let's say, plus VSAT, it will go to minus VSAT, stay there for some short time and then come back up and stay here indefinitely. So unless you do something that it always stays in one of these two states, either you could design it to stay in plus VSAT or to minus VSAT. But when you do something, it will change, go into the unstable state, which is this one, stay for some time, and then come back out. And then the bistable stays. If it's in VSAT plus VSAT, it will stay there indefinitely. If you trigger it or you do something to it, it will go and stay in the other state indefinitely. If you do something to it, it will come back, right? If you do something to it, so you could do all sorts of things with it. But all of these changes all of these changes, you have to actually trigger. If you don't do anything, it will stay in whatever state it is forever or until you turn off the power. Okay? So let's have a look at them one at a time. The first one there, stable, is a square wave generator. We've spoken about square waves already, and we're going to meet it elsewhere too when we talk about the Fourier series and Fourier transform and some of the effects of the square wave. So this now is a device, is a circuit. You have an op-amp and you have some resistors and a capacitor in it. First off, if you look at it, there are no external inputs. So we have a capacitor, we have a capacitor C, and we have a resistor R here. And then notice those are connected. So C is connected from the output of the op-amp, right? So it charges. In other words, C will charge or discharge through RF. And C, the voltage on C is connected to the inverting terminal of the op-amp. The non-inverting terminal of the op-amp is connected via a little potential divider. So there's a voltage coming back here that is a fraction of the output voltage. So it's V out over R1 plus R2 here, right, multiplied by R2. So a part of V out is whatever V out happens to be, a part of it is fed back to the non-inverting input of the op-amp, right? So let's see what that does to us now. If you look at the circuit, we switch on the circuit. So at some point in time, let me just get a different color here. Blue. So we switch on the circuit and the capacitor is discharged and the output voltage is 0. Right? So for a brief while, the output here is 0. So this is 0 volts here. Here is 0, the capacitor is discharged. But for a brief, because of leakage currents in the circuit, remember all of these circuits are not ideal. There is small currents that will be flowing around. The voltage on the the voltage on the capacitor starts to change. It starts off at 0. Here is supposed to be at 0 volts, but because of leakage currents, small leakage currents in the circuit that exist just because the circuit is powered on, this voltage now changes. Remember, here is at 0. So this voltage here, the voltage on the capacitor changes, and the little leakage current starts to increase this a little bit. The capacitor starts to try to charge. The instant that charges now, this point here, you remember what the op-amp is, this is the inverting terminal. So the instant here gets more positive, the inverting terminal gets more positive than the non-inverting terminal. The output here is an inverting arm. So if this goes more positive than this, the output is going to saturate negatively. It's going to invert and instantly go down to minus V sat. Right? So now the stable starts to work. Once here is at minus V sat, if here is at minus V sat here, then this point is a fraction of that according to this. So V out is minus V sat. So some fraction of minus V sat appears here. Okay? And we'll see what to call that in a little while. So here is at a negative voltage because but not the full V sat value, right? So the capacitor now starts to charge. If here goes negative, the capacitor starts to charge negatively to whatever voltage this is through RF. So it's charging, and this voltage gets more and more negative. So this voltage is going to drop. Eventually, this voltage is going to get more negative than that voltage. Yeah? This is the capacitor voltage here, VC. So the capacitor is charging negatively, right? At some point in time, it is going to reach a value, right? Whatever this is, minus V, I'll call this minus V1. You'll see what it is in a second. At some point, this one is going to get here because the capacitor is charging towards minus VSAT. At some point, the voltage here is going to get more negative than the voltage at the non-inverting terminal. If that is the case, if here is more negative than here, the output is going to saturate, but in the opposite direction because there's an inverting terminal. So the output now at this point, right, which is where the inverting terminal is more negative than minus V1. Right here now, the output now is going to change from minus VSAT suddenly to plus VSAT. Right? So this now becomes, where we are at here, we are, let me just find my, say here. So this point now becomes positive VSAT. Here becomes, we have positive VSAT here, so we have plus V1 here. And you remember, C was on a negative charge, but because here is now positive now, it starts to discharge and starts to charge back positively. So it's charging now. It's charging back from a negative voltage and it's charging positively. Sometime here is at plus V1. At some time as the capacitor charges now, here is going to get more positive than here. Again, here, this voltage at this terminal is going to increase past plus V1. If here gets positive, it's on the inverting terminal, the output is going to go negative. So it's going to, at that point in time, the output slams down to minus VSAT now. And then the cycle starts to repeat. Once you're at minus VSAT, the capacitor will discharge again and then start to charge negatively until the voltage reaches, when this is negative, this will be minus V1, and then it toggles again, and so it will keep going on. So you're getting this square wave behavior, the capacitor charging, discharging, charging, discharging. Everybody following that? Make some sense? Yeah?
So do you mind going over in terms of
which part?
So when one input either becomes more positive or negative, what will happen again?
Okay. Look at the other slide. Okay, I'll get to this in a second. So let's go back here and start fresh, right? Good. So at the point I've switched on the unit, we assume that the capacitor has 0 volts. So when I just switch on, I have 0 volts here. The capacitor is discharged, the output is discharged, right? Because it's electronic circuits that we're dealing with, these voltages, they are very small leakage currents around. And what's going to happen is that the capacitor voltage is not going to remain at 0 for any length of time. It's going to try to increase very slightly because there's leakage current floating around in the circuit. Microamperes, picoamperes, it's very small, but it is there just because the circuit has to operate. At that point in time, we turn on the circuit, and the instant here goes positive. Now, when the capacitor was at 0, we assume that it was at 0. The instant it increases a little bit above 0, the output was 0, so all here is 0, all here is 0. If this voltage goes to, let's say, 0.1 volts, just for argument's sake, 0.1 on the inverting terminal, that is more positive than the non-inverting terminal. So it is, there's here's more positive, but is an inverting terminal. So if here is more positive than here, or the value of the voltage here is greater than here, the output of the op-amp is the inverting terminal will try to go negative. Fair enough? Remember that's how an op-amp, huh?
Yes, sir.
Good. So at that point, we know the op-amp drops down to this point, minus VSAT. So once here goes from 0 to minus VSAT, here now is some part of that, as we saw, is minus VSAT by R1 over, sorry, by R2 over R1 plus R2, right? And I'm calling this, let me just call this minus V1. So here is now minus V1. If here is at minus VSAT, which is this bit here, the capacitor now starts to charge to that voltage through this RF. Here's minus VSAT, so the capacitor will charge through minus VF to try to get up to minus VSAT. All right? And once it's doing that now, this voltage here now, at this point, is going to be falling because the capacitor is charging negatively, right? So it's good doing this. At some point, the voltage here on the capacitor is going to get more negative than V1. So let's say this is minus V1. This is going to be minus V1 plus, sorry, more negative minus, let's say another 0.1 volts, just to use a value, right? It goes a little bit more negative than minus V1. Again, we're dealing with an op-amp here. So if this is more negative than here, the inverting input is more negative than the non-inverting input, the op-amp is going to invert that difference and amplify it. So it's going to, here is more negative than here, it is going to send the output positive. It's going to invert. So at this point in time, the output now is going to go from minus VSAT, it's going to shoot up to plus VSAT. That makes sense?
Yes, sir.
Right? So now, at that point now, here's plus VSAT. This point here now becomes plus V1. We haven't changed the resistor, so it will be just the positive version of what we had. Here's plus V1. And the capacitor now starts to, it was at a negative voltage, so it starts to charge back up positively now. So whatever it had there, it starts to charge until it gets to the point where here is now plus V1, plus a little bit more than here. Here is held at plus V1. So as soon as this point shoots up past V1 now, the inverting terminal is more positive than the non-inverting terminal, right? The op-amp, because it's the inverting terminal, the op-amp is going to saturate, but to the opposite side. So it's going to move from VSAT to minus VSAT now. And when you do that, the whole cycle repeats itself. So here's minus VSAT, here's minus, here's minus, here's minus. And then the capacitor now starts to discharge and charge negatively. And as soon as it gets a little bit more negative, then the op-amp is going to flip to the positive. So it goes from minus VSAT plus VSAT minus VSAT plus VSAT, right? And the only thing now, what you have control over, this is the charge and discharge of the capacitor. Now the capacitor is charging through RF and discharging through RF. So the bigger RF or C is, the bigger this charge and discharge cycle will be, so you can actually adjust the timing of the square wave. Unless so that's clear right now, we'll get to the little arithmetic in a while. But everybody understands the operation?
Yes, sir.
right? Remember that the basic thing with an op-amp, right? You have negative, positive here. If the inverting terminal, the magnitude of the voltage of the inverting terminal is bigger than the magnitude of the non-inverting terminal, right? If this is bigger than this, the output is going to go negative, all right? And once you keep that in mind, and if this one is bigger than this, the output is going to go positive, right? That's how the circuit is working. So let's see the little arithmetic behind it now, right? The arithmetic behind it is, first off, the actual voltage. We saw that that threshold that I was, or the little voltage that I was calling V1 and V2 is plus or minus Vsat by R2 over R1 plus R2. If the amplifier and the assumption is that Vsat is the same value, positive and negative, for most amplifiers it is, then the little value that I'm calling plus V1 and minus V1, they actually have a terminology for it. The positive V1 is what you call the upper threshold value. That's this, right? So that is the value when the capacitor charges, and as soon as the inverting terminal hits that, the upper threshold, the multivibrator switches from plus Vsat to minus Vsat. And then the negative one, what I was calling minus V1, we call V lower threshold, LT, so that the capacitor discharges, and once it becomes more negative than the non-inverting terminal, or flip it around, that the non-inverting terminal is more positive than the inverting terminal, then at that point, the op-amp switches back from minus Vsat to plus Vsat, right? This ratio of R2 over R1 plus R2, in the literature, they give it a Greek letter, they call it lambda. And the timing, which is the total period, which is this one full cycle of the square wave, one full cycle, which is this. Oh, I'm cooking on this side, but anyway, because of holding a pill. That time is given by 2RC. This is a natural log, 1 plus lambda over 1 minus lambda. And lambda is this, the relationship between that potential here, R2 over R1 plus R2, right? Why this comes in, you remember the charging for the voltage across a capacitor is this e to the minus t over RC bit, you remember that? So it's an exponential charging. So if you want to solve for t, you have to take a natural log to get rid of that. But look at this strange thing. What happens if you have a calculator on you right now? Tell me what happens here if, very quickly, shouldn't take more than a minute, if R2 is equal to 0.86 R1. Tell me what happens. R2 is equal to 0.86 R1. Anybody with a calculator? Work out lambda and then tell me what this is. If R2 is equal to 0.66 R1, what does that do? Anybody has any idea? If you work it out, if R2 is equal to 0.86 R1, you're going to get that here, inside of here, is going to be 2.7, I think it's 2.718. And if you take the natural log of 2.718, right, remember this is E. So in other words, when R2 is 0.86 R1, 1 plus lambda over 1 minus lambda is E. And so that the natural log of E is 1. So in other words, T just becomes 2RC. Yeah? You hear me all right? There's some heavy rain is falling here. Just let me know if I need to speak any longer. Everybody following that? Huh?
Yes, sir, we're hearing you.
Okay. Right, so just a little design. You don't have to do it, but if you happen to pick, I mean, this is a funny little, a funny ratio here. If you happen to be able to choose R2 to be equal to 0.86 R1, so let's say you pick R1 as 10K, then R2 will be 8.6K. If you do that, then the timing, the period of the oscillator will just be 2RC. So you pick the capacitor and then you pick the value of the RF, right? It should be well, I guess 2RFC inside of it. Right, so everybody following how the stable multivibrator works. Yeah? 1, yes, somebody said 1. Nice, correct. So the log part will work out to 1, very good. Okay, so that's a stable. As I said, it changes state at a predetermined rate determined by the value of C and RF. Okay. The other circuit now in the arsenal is a monostable. This is the one that is stable in one state and will stay there indefinitely until you do something. Now, this one, the length of time it spends, again, is only dependent on 2 components, 1 resistor and 1 capacitor. The rest of the circuit is just to keep it in a particular state for a particular time, all right? So this is the circuit here. And if you look at it, the circuit looks a little bit complex, but let's just watch something, break it up a little bit. The block in yellow, or whatever color it's appearing, this is basically what we had in what we just discussed. And we had the capacitor here, right? We had put the capacitor C here. So what we just discussed, a stable multivibrator, we have the capacitor in the circuit, and we get the unstable behavior. What I do now, the same capacitor, let me just erase that here, right? Notice that same capacitor is here, right? I'm just broke up the circuit a little bit. Yeah, pen. So this, if you ignore everything else so far, if I attach this here, forget the diodes and every other thing, this circuit without the diodes is what we just spoke about. So what I'm going to do, I am adding some components here now. I'm taking a diode and connecting a diode across the capacitor. Note that the cathode for the diode is connected to ground. Right, so the same capacitor that I had before, I now basically bypass the capacitor with a diode. The diode is connected to ground. On the non-inverting terminal, I have a little trigger circuit, which is a capacitor, a diode, and a resistor, right? A small capacitor, a medium-sized resistor, and this diode here. right? And I'm connecting that. This is going to ground. What happens here now? This kind of circuit here, let's see what, we will get to the behavior of the circuit in a second. We saw that this circuit, if I without D1, is they are stable. So it is square waves all the time and just determined by the value of the resistor and the capacitor. Once I put these additional components in it, let's see how the behavior, what happens. There are three particular states of it. One is a stable state where it will stay forever. The other one is a transition state, and then the other one is a timing state, right? This is the unstable state, right? This one is unstable. So it's going to stay here for a little while and then return to the stable state. So let's assume that we are in a stable state where the output is at plus VSAT. Okay, so we are, this is the output here. The output is at plus VSAT. If the output is at plus VSAT, here, if here is plus VSAT, this is our capacitor here. Notice that as soon as here goes positive, above 0.7, this diode is going to start to turn on, and it's going to keep here at 0.7 volts. So once here is at 0.7, right? Forget these for the time being, okay? So ignore all of this. This is irrelevant. Once here is positive, right? Here, the capacitor voltage, it will start to charge the capacitor. And as soon as the capacitor voltage gets more than 0.7 volts, D1 is going to turn on and keep here at 0.7 volts. Yeah? Everybody see that? Then we also saw, this is the same little feedback circuit that we had in the stable state. Here, this point here is at a fraction of VSAT, right? And because it's a positive, this is V upper threshold, which we just saw. So here's at V upper threshold, some positive value. Here is at 0.7, right? Remember the op-amp tries, all the operation that the op-amp does is to try to make these two voltages equal. The op-amp, the diode here is preventing that. Here's at V upper threshold, whatever that is, and the diode is keeping here at 0.7. So the op-amp is churning out current, trying to correct that all the time, and it can't. Because of that, this point, the non-inverting terminal is more positive than the inverting terminal, so that the output keeps at V saturated all the time. Following that? Everybody seeing that? Yeah? You all right? Speak to me, let me know. Somebody?
Yes, sir. Good.
Yes, sir.
Right? Okay. So once the output here is at VSAT plus VSAT, this thing is going to stay there indefinitely. Right? It's nice and it's happy. Let me now put an input at the point of the capacitor diode at these little three components here. I am going to send V in to a negative voltage of at least, yeah? Somebody had a question? Okay, I'm going to send a negative voltage on this input here, going down to at least minus V upper threshold. Remember here is at V upper threshold here, right? Which is, well, we take that as positive actually. So I'm going to set a voltage here. I'm going to send a voltage at the input that is going to go negative by at least in the minus amount of V upper threshold. As soon as I do that, notice what happens. If here goes negative, if here goes negative, sorry. If here goes negative, then this point, remember here was at some point in time positive, right? Just now, half a second. As soon as Vn goes negative, at some point in time, here was positive, so this diode now becomes forward biased. As it becomes forward biased now, if here is pulled negative, then here doesn't have a choice. The diode is forward biased, so this point now suddenly goes negative. Everybody following that? So here is, I pull this negative, here is going to be pulled negative. So I'm now getting into a transition state. If I pull here negative, remember at the point when I pull here negative, here was 0.7 volts. Because here briefly is more positive than the non-inverting input, the op-amp is going to go from plus VSAT to minus VSAT. So here is going to go down to minus VSAT. So at that point, once I put the negative input here, V out goes to minus VSAT, and then notice what happens. If here goes to minus VSAT, here is now negative, so that this diode is now reverse bias. Because of the same virtual earth behavior that I spoke about, here is going to go negative, so this diode is now reverse bias. So both of them are now out of the circuit. And like we did for the precision rectifier circuit last week, let's erase them. So this is what the circuit now looks like. Everybody following? Yeah? No, you want me to go over anything?
Yes. No, sir, you're good.
Hmm?
No, sir, you're good.
We're okay, right. I guess I could replay the video. Anyway, so this is what happens. So at that point in time, once I've put the negative voltage here, the output now goes to minus VSAT, and the two diodes come out of the circuit. And in fact, this is what the circuit now behaves like. So we have minus VLT here. And if here's VSAT now, the capacitor is now going to start charging negatively through that resistor. The diodes are not in the circuit, so the capacitor starts charging negatively through the resistor. And at some point in time, this voltage here is going to exceed, because it's charging, remember, it's charging negatively towards minus VLT. So if this is minus VLT, and as we said, as soon as this gets a little bit less than that, right? So minus VLT minus some delta V. Then at that point in time now, this terminal is now more positive than that. The output of this is going to shoot back up to VSAT, which is the stable point. So this only stays in this negative thing. It was stable. We put the trigger, so it was at plus VSAT. We put the trigger and it goes to minus VSAT. In the minus VSAT stage, it charges through the capacitor C, charges through RF. So whatever is that time constant behavior, it charges. And then as soon as it reaches that point where it charges to a little bit more negative than VLT, the circuit goes back up into the stable state and changes, right? So you get a pulse. The circuit gives you a negative going pulse of some duration, and then will return to the positive or stable state. It has completed the output and is now back ready to work again. All right? So this is how it is, the trigger pulse. that negative going pulse here, right? The negative going pulse is what starts everything in motion. And then having done that, it stays negative for a while, and then it comes back up to the stable state, right? And again, the relationship is a charging and a discharging of the capacitor. Remember the capacitor, unlike the first case where the capacitor goes between the V lower threshold and the V upper threshold, when the thing is in the stable state, the capacitor is charged to just 0.7 volts. The diode in the circuit here, in the stable state, the diode keeps the capacitor at 0.7 volts. So in the stable state, VC is 0.7 volts. In the unstable state, it goes down to minus V lower threshold. And the relationship, again, the timing relationship for that, how long the pulse is minus VSAT minus 0.7, which because the capacitor starts at that, over minus VSAT minus the lower threshold value. And again, we're not going with the derivation of it. You're dealing with a capacitor. So again, you're dealing with a E to the minus T over RC charging business. So you have to take a natural log to get rid of that. So the actual timing constant, you know this. This comes from the spec, right? Plus or minus like 1 volt within VCC, 0.7. And V lower threshold, you remember the threshold is this resistor value here. So the threshold is minus VSAT over R1 plus R2 multiplied by R2. Okay, the same principle. So once you understand the first one, they are stable. This one is the threshold values are exactly the same, right? And it comes back then it reverts to the timing, right? So I have the two waveforms here. And the last one now, okay, let me just talk a little bit about it. So the circuit, now, what happens is that, remember, when it goes negative, we have to wait until a little time, until when this goes back to the plus VSAT, it takes a little time for here to get back to 0.7 volts, right? That time is called the recovery time. So until that happens, you can't send a multivibrator to generate another pulse. So there's a little time delay. What they sometimes do is to put an additional resistor and diode to help the capacitor discharge faster. So once it's discharged, to get it back to the 0.7 volts, because here's plus VSAT, they put a diode in the circuit that actually bypasses this big resistor with a smaller one. So you actually charge back up the capacitor quite quickly. All right? But it's not, you don't have to remember that. What I'm more interested in is in you understanding how the circuit works. Okay? And then the last multivibrator circuit is the bistable. This is the one that will stay in some state until you tell it to do otherwise. So for instance, if the state happens to be minus VSAT, then the output here is at minus V lower threshold, which is minus VSAT by R2 over R1 plus R2, okay? So this point is at minus V lower threshold, minus whatever that voltage happens to be. If I were to make now to send a voltage here that was more negative than this, right? I send a voltage that is more negative than this, then what is going to happen is that the output here, if here is more negative than the non-inverting terminal, Or if you want to put it the other way, the non-inverting terminal is more positive than the inverting terminal. The output here is going to shoot the VSAT, plus VSAT. So at that point, if I put a negative voltage here, the output is going to go to plus VSAT. And then to get this to go to the other way now, I have to put a positive voltage here that is greater than this value. And then when I do that, if here is more positive than here, the output is going to go to minus VSAT. And it stays there, right? It doesn't move until you tell it something. And we know it from electronics. This is a type of circuit that we call a flip-flop. We know it from digital electronics. We know that the output will either go plus 1, 0, 0 plus 1, that kind of thing, 1, 0, 0, 1, depending on what you do. All right, but the electronic version, remember this one now is going with plus or minus VSAT, which is a positive and a negative voltage. But this one will stay in there indefinitely until you do something, right? So the progression again is first you have a device that is not stable in any state at all, right? It's not stable in any state. So once it enters one state, it stays for a little while and changes to another state, and stays for a little while and changes back to the first state, and it will keep going back and forth. That's a stable multivibrator or a square wave generator. The second one is where it's stable in one state. So it will stay there all the time. But if you give it a negative going pulse, it's going to go to another state and stay for a while. And then as soon as a capacitor charges up, it's going to switch back to the stable state and stay there again until you do something. And then the last one is a bistable that will stay in whatever state it is indefinitely. If you don't do anything, it's going to stay there forever. So if it's in VSAT and you do nothing, it stays there. If it's in minus VSAT and you do nothing, it stays there. But how we get it to stay is by putting a suitable polarity voltage on the output. All right? So if it's on positive, if the output is positive and you want to change negative, you have to make this terminal here. You have to put a positive signal on the inverting terminal that will send the output negative. And when you want the output to change again, if you put a negative going to signal on the output, the signal is going to, the output is going to go back positive again, right? So depending on the polarity of the input, you can change the polarity of the output, otherwise it will stay there forever. Make sense? Yeah? Maybe?
Yes, sir.
Some of it you have to, again, some of this stuff you have to look at it carefully, listen to the recording, or just watch the notes and play with the values a little bit, especially this one here. Just play with the values. Start by assuming something on the output. So if the output, and if you don't like to use plus VSAT or minus VSAT, say, okay, the output is at 10 volts. If the output is at 10 volts, here is some fraction of 10 volts. Let's say we're looking at this thing, let's say here's at 3 volts. If the output is at 10 volts, positive, because of the positive here is going to be at 0.7 volts. So 3 volts is more positive than 0.7. This is going to stay at 10 all the time. If I make V in negative by more than 3 volts, so I have to, because I want to make sure this turns on and goes negative. So if I put here by at least minus 3 volts, this diode turns on. If here is at minus 3 volts, it means that the output here, if this is at forward bias, it's going to try to come at minus 3.7. If here is at minus 3.7, here is automatically going to become minus 3.7. Just to put numbers in the circuit. And if here is at minus 3.7, this diode is now off the circuit. This diode is now out of the circuit because it will now be you remember I sent this like this, so I just sent it to -3 volts and brought it back up to a positive value. So here is now reverse bias. Here is now reverse bias. You could take them out of the circuit like this, right? And analyze the behavior now, right? And it will convince you, as I say, instead of using -VSAT, you could put some numbers in there just for the time being and so on, but get used to using the variables instead. And once you do that, then I think the rest should follow suit. All right. Okay, so just a couple of announcements before I end. Tomorrow, the second half of the class, we'll have a tutorial on problem set 1. So if you haven't done so already, at least look at the problem so we could talk about, you'll have the solutions, I'll put up the solutions for you, but the class is really one, if there were any errors in my handwritten solutions, where they may be when I was writing it up, or if you're not too sure how to address or to answer the particular question at hand, to come with a question. So that's what the tutorial is about. All right, not so much me working out each and every problem on the board, right? But for you to come with your question, so it only makes sense for you. You will get more out of it if you have a look at the problems and at least try to attempt to answer the problems before the tutorial, right? So that's one. And then the midterm, right? I see some people kind of left already. So I'll put it on the announcement, but they could have heard it live. The midterm is going to be Tuesday, the 25th of October, right? Don't know if anybody else has anything. So I'll put that on there. I'll let them know in the department to make sure that it doesn't clash with anybody else, right? But Tuesday, the 25th of October is when I'm going to have the midterm for you. Okay, so it's going to be right now it looks like it's going to be probably a 60-minute test in class, and you could work with it. I'll let you know the format most likely will be 60 minutes with open book, so you can do some things like that. All right, okay, fair enough. All right, so let me ending the recording.